The next part is going to be this proportionation. I've got some hydrogen peroxide, and you can barely see the equation that I have up here. I'm going to get a better magic marker for this. But this has got hydrogen peroxide making water and oxygen. By the way, this is 0.88 molar Swan hydrogen peroxide, 3%. It's what you would get at any pharmacy. In fact, it's called 10 volume because 10 mLs, or I should say 1 ml of this hydrogen peroxide will end up making 10 mLs of oxygen. If you go to a hair salon, they'll have 40 volume, where 1 ml will make 40 mLs of oxygen gas. That's 4 times more concentrated. Now, is there anything wrong with this equation right now?
It's not balanced.
You're right. It's not balanced. We've got 2 oxygens, and here we've got 3. And I hope by now we've done this one often enough that you realize we're going to need a coefficient of 2 here and a 2 here, and our reaction is now balanced. In terms of atoms, we're now fine. So 2 molecules of peroxide will make 2 waters and some oxygen. What is the oxidation number of the oxygens in peroxide?
-1.
Beautiful. That's one that's worth remembering. It's a very reactive molecule. What is the oxidation number of oxygen in water?
-2.
-2.
Beautiful. And what's the oxidation number of oxygen in oxygen?
0.
0.
0. Right. So we've got this peroxide, and it both reduces, going from -1 to -2, and it oxidizes, going up the number line from -1 to 0. Hydrogen peroxide is capable of oxidizing and reducing itself. And that makes it a bit dangerous. The reason they don't sell more than 3% is because hydrogen peroxide can react with itself and turn into this huge volume of gas. In fact, if you have 40 volume, 12% hydrogen peroxide, you can't send it out on an airplane. You've got to ship it because it's just too explosive. In fact, when you buy the stronger versions of this from science companies, they will have a special cap that will let the gas release, because if it does decompose, the pressure will build up and the bottle will explode. So I've got this here. We know it's an oxidation reduction reaction where hydrogen peroxide can react with itself. It's a self-contained reaction. Peroxide has an enthalpy of formation of -190 kilojoules per mole. Look that up. Water has a enthalpy of formation of -290 kilojoules per mole. Water has less potential energy than, well, I should say, okay, so we've got those two. What's the enthalpy of formation of oxygen? Don't tell me I've stumped everybody. The
0.
delta, pardon?
It's 0.
Exactly.
Require no element.
Yeah, all elements, if you make them from elements, have a 0 kilojoules. Now let's figure out what's going to happen when I start reacting this hydrogen peroxide. 2 of the peroxides, 2 times -190 is -380 kilojoules. Then we're going to make water, which 2 of which would be -580 kilojoules for this reaction. Of course, oxygen is 0. It releases 240 kilojoules of stored energy. Let's watch it. Here we go. I'm going to get a bunch of hydrogen peroxide. In fact, actually, yeah, I can pour it out. This has a cap that would release pressure in case it's there to decompose on its own. Here's the stuff, hydrogen peroxide. Oh, so exothermic, that means it's gonna, that is thermodynamically favored. What about the change in entropy?
It's also entropy favored because it's making gas where there once was just liquid.
Right, we're starting with a liquid, we end up with a liquid and gas, we also have more molecules, both of those. If somebody said, what are two things that would favor the entropy? The gas, definitely, that's dispersed matter, and also greater number of molecules. Those two things would be the two answers. So that's probably worth remembering. So this is favored by being exothermic. This is favored because it increases the, I shouldn't say randomness, it disperses matter. It is thermodynamically favored, but nothing's happening. I mean, it's got everything going for it. It can react with itself. It releases kinetic energy. It becomes lower for potential energy. And I mean, this is ready to go, but nada, nothing.
Add some magnesium. Isn't that what reacts with it?
No. In fact, save that. Let's see. Darn, it's 20 minutes. No, remind me to do one reaction. Oh, I'm so glad you mentioned magnesium. Okay, that's gonna be one of my, because even though I love this. So why isn't this a reaction occurring? But I mean, you're on the right track.
Do we need heat to meet the activation energy?
Oh yes, if we heat this is gonna happen. Because we'll have molecules moving faster. These guys will smash into one another with greater energy to get up to this activation energy and go through whatever mechanism it goes through and makes our product. But I'm not going to.
Is that why it works best in sunlight?
Yes, in fact, that's why they use it. That's why this is in a dark bottle. Every one of these things will be in a dark bottle. So photons of light, if they're absorbed, can kick this up here. So kinetic energy, heat, a hint. And another hint. Turnip and yeast.
You need a catalyst. Yeast
for room temperature, the kinetic energy, this barrier is too big. A catalyst provides an alternate method that makes it easier to make that first step. And yeast has an enzyme in it, peroxidase. And peroxidase, an enzyme, is set up so that when hydrogen peroxide molecules make contact with it, they're kept in place so that they are oriented so the collisions are more effective. The answer on a FRQ, what does a catalyst do? It provides an alternate easier, I shouldn't say easier, lower energy pathway. So here's my yeast beasties in there. They're little peroxidase, and voila, we get fizz. In fact, this thing is going to overflow. I better get myself, I better get myself something to catch this. And where is my, there, in case it does overflow. Very, very effective. Yeast has peroxidase. Those of you who are into CSI, what other substance is very good at acting as a organic or enzymatic catalyst? I'm surprised no one knows that. Has anybody put hydrogen peroxide on a cut? Because that's what very often this is used for.
Yeah, I've used that a lot.
Yes.
It hurts so much.
Oh, it does. And what happens?
It eats away at your skin cells, right? And all the other cells.
Yeah, I mean, because of this oxidation reduction, you've got some intermediates here that are very, very, very reactive, and they'll react with things. But why does it start to fizz when it makes contact with blood?
Because you have a catalyst in your blood, the same as the yeast.
Yes, your blood is a catalyst for this reaction. And if I were a really, really dedicated chemistry teacher, I'd I'd get a drop of blood and put it in here, and you would see it fizz just as well as with the yeast. But instead, rather than getting blood from your chemistry teacher, turnips surprisingly have peroxidase in them. And you say, okay, this should be fizzing. And if you look carefully, you'll see a little bit of fizzing there. Now, we're talking about reaction rates again. And So blood, you can't get blood from a turnip, you can get peroxidase. So what I'm going to do right now, oh, wait a second, hang on, I should get a beaker to catch this with. I got my microplane grater. Oh, if you do any cooking, you need a microplane grater. They're just amazing. And I'm going to catch my turnip shavings. By the way, turnips are an excellent food. They're sweet, they're flavorful, and now I'm getting a lot more bubbling. What effect was this in terms of reaction rate? Why am I getting more bubbling now than tossing those peels in?
Because you're increasing the surface area and you increase the concentration.
Oh, yeah. I'm not sure about concentration. I would say surface area. That is good. Concentration, because we have a solid, I don't think so.
Oh, okay.
Maybe there's also some juice in there. So, one of the things on CSI, they use hydrogen peroxide to detect blood, and they mix it with luminol. I'll do that in a later experiment, maybe, where when the hydrogen peroxide reacts, it makes the luminol glow, and you can detect photons very, very easily. So if you want to make a crime scene look like it has blood, even though it doesn't have any, you could use turnips, or you could use yeast. One extra little thing. Are we running for time? Okay, we're okay. I'm going to pour out some more hydrogen peroxide.
I don't see a Brookie in your contacts. Who do you want to FaceTime with?
Siri, stop. Somehow Siri thought I was asking it something.
Okay.
Here I have some more yeast, and I'm going to pour it into here. It clouds things up, but I don't get any fizzing. Yet that's yeast. The difference is I poured boiling water on yeast. The enzyme, the peroxidase in yeast, is a folded protein. Why does boiling water mess up yeast? So that
Because it denatures the enzyme.
beautiful. Oh my gosh, that was excellent. Love it. Yes, the heat, the enzyme is held together by hydrogen bonding in its shape. The enzyme is still there. Its molecules are just the way that they used to be. But the hydrogen bonding that has kept the shape of this yeast molecule, this peroxidase, has been messed up, and enzymes work because of their shape. And if you mess their shape up, denature them, like cooking an egg, that's what cooking an egg does. It doesn't destroy the egg, it just unfolds those proteins and denatures them. So when you're cooking, you're denaturing. Also, this is one of the reasons why fevers can be very dangerous. You have so many enzymes in your body that have these multi-step processes. If you get too hot, you're in trouble. You may be preventing these enzymes from working. So here we go. We've had our yeast. We've got our turnips. You didn't get my blood, but we still have more hydrogen peroxide. Let me get another setup right now. Give me a second. Chat with one another. And if you've got any questions, put them out there. Ask me.
If you put too hot water on yeast when you're trying to make bread, it won't work. And then you'll have super flat bread and then it's terrible.
Yeah, it's happened to me before.
Also known
Yeah,
as
me
waffle.
too. In fact, they say very specifically, don't get the water hotter than 100 degrees. And like you say, you have unleavened bread should you end up getting your yeast too hot. Yeast and enzymes are delicate. Too much salt. Well, I'm not sure about salt, but in terms of heat, that temperature, they've got a very specific set of instructions. And here, let me get this set up. This is the
My hydrogen peroxide says it's stabilized. What does that mean?
Oh, I'm sorry you asked. Not sorry. because it decomposes so quickly, if you buy some concentrated hydrogen peroxide, they got to make it safer, and they toss in a stabilizer. And the weird thing is, I don't know how that stabilizer works. I was going to look that up before we started, and I'm pretty sure they use tin ions. And I'm not sure why tin ions would end up stabilizing hydrogen peroxide. My guess is it prevents one of the steps in the reaction mechanism.
Does that mean my hydrogen peroxide's less fun to use now?
If it is stabilized, yes. Now, food grade, well, it depends what your fun is. Okay, food grade hydrogen peroxide, I think, is not stabilized. The stabilized stuff is usually, in the meantime, let me get this going. Let's see. I've got, by the way, bleach also ends up acting as a catalyst. I found out when I didn't clean out one of my graduate cylinders and it had some bleach in it, and man, the peroxide decomposed. Some bleach into some food dye. And we'll keep this at the side. And I'll talk about that later, because that's going to take some time. So right now, I've got a lab setup. Let's see, how are we set there? I can't see. Does it look like everything is visible? Except for the bleach.
Yeah.
Yeah.
Good, good. Okay, I'm going to get some water, because again, I can't see what's happening here. And I'm going to fill up this graduate cylinder. Hold it in my hand, flip it upside down. This is, they sometimes refer to it as a water trough. This water in the graduate cylinder is attracted by gravity, of course. Here's my ring stand, standard in all chem labs. Why doesn't this water come pouring out? It's upside down. I let my hand go.
There's pressure in the in the tub preventing it from going all the way out, right?
Yes, atmospheric pressure is pressing down on this water. If this water, if I drilled a hole on top of this graduate cylinder, then that pressure could go here and this whole thing would flow out. Yes, our atmospheric pressure is pressing down, and our hydraulic pressure, excuse me, tip this water, it'd be a mess. Live theater, folks. Or if I were working in a vacuum, there wouldn't be any pressure, and that water would just come pouring out. And in the meantime, I'm getting this hose. Oh, stop. Oh, air came in through this. I was too low. Lord. I should have kept that up there. I'm gonna have to refill this and get this experiment to work. Live theater, certainly improv, and air pressure, good example of siphoning there. Air managed to get in. I didn't want any air to get in there. Instead, I wanted this to collect oxygen. I'm gonna flip this over again, put it up here, and this time I'm gonna secure it. Okay. I've got to keep this hose end higher than here. Oh, it almost fell. Oh, I have to do the whole thing over again. Hydrogen peroxide time. Oh, I should have only hit. Oh, speaking of this, hydrogen peroxide in my clean beaker. If you have a dirty beaker, or if there's some yeast in there, this whole thing would be gone. Next, speaking of air pressure. When I was in school, high school, even in college for some time, we always pipetted by mouth. This is a pipette, graduated 0 to 9. This is a pipette bulb that I can crush. Step 1, crush the pipette bulb. Step 2, siphon up the hydrogen peroxide, because I need 9 mLs exactly. Step 3, this has got a side thing that lets air come in, and your hydrogen peroxide from 0 to 9, I've dispensed 9 mLs of hydrogen peroxide, which is 3%, 0.88 molar, into here. The pipette bulb that you see here is probably going to be out of date soon. If you work in a good college lab, they'll have a digital pipette for you. And not only will you not be pipetting by mouth, that's how I found out acids were sour. I just transported to this side. Flask, everything is hooked up. And I'm going to need somebody to be a timer, maybe. Yeah. If somebody would end up being my timer, and when I say time, give me the seconds. And anybody is going to volunteer.
I have a timer.
Excellent. Okay. I'm sorry, I didn't recognize the voice.
Lily.
Lily. Okay, Lily. Excellent. You're the timer. And here I've got 0.6 grams of potassium iodide, which is an excellent catalyst. There are a lot of catalysts for hydrogen peroxide. Potassium iodide, Ki, is one of them. And this one's good because I don't have to worry about heating, because this is an ionic compound and I'm not going to denature an enzyme heating it, so that's not going to be a problem. And I'm going to dump this in here, dissolve it quickly. And Lily, start timing. Oh, wait, no, don't start timing yet. Don't start timing yet, because we have to wait till I get some bubbles coming through. It turns sort of yellow. There's an intermediate in here that okay, there we go. Start timing. Here, we're getting our oxygen collected by water displacement. This is a classic chemistry technique that goes all the way back to, Pascal even did this. This goes back to the 1600s. The potassium iodide, you started the timing. Good. Now I'm going to leave it alone. The potassium iodide is dissolved, and we're getting bubbles of oxygen coming up here, displacing the water. And we've collected 10 mLs, and I'm going to say, give me the time at 20. So I'll put this here. In the meantime, somehow there's a mechanism that is involved. You can see that a little bit better with that background. 20, time. What was the time?
54:49.
Okay, let's make it 54, because, wow, down to the 100th of a second. 54 seconds, that's as good as we're going to get. That was 20 mLs. Now, I'm going to record the volume at 20, 30, 40, 50, and 60. I've got a table down here, and I have my trusty lab book that I always have with me when I'm doing a lab. Whoops. 30. Oh, darn, I missed 30. Talking too much.
Should I still be timing?
Yes. Okay, time. 40. What's the time? At 40?
Lily, you're muted.
Oh, we missed it. Here, let's, we have the time then maybe at, not yet. $50. What's the time? Lily.
I don't have it. It stopped timing.
Oh,
I stopped timing it.
So we'd have to do this experiment over again had I not done this experiment ahead of time. In fact, this is good because we didn't want to wait to get all the oxygen in there. It'd take too much time. Oh, Tom, we're running out of time. I still want to do my favorite experiment. I'm going to bring it up right now, share screen.
Excuse me, Mr. Muscalock.
Yes?
I don't think you were clear about telling Lily how long to time and when to start and when to end.
Yes. Poor instructions on my part. I should have given better instructions. That's fine, Lily, because actually I'm glad we didn't have to go through the entire experiment. If you had, I'd be here still counting stuff and we'd be looking at little bubbles. But I've just brought up my spreadsheet from the experiment I did the other day, yesterday, in fact, where if you look here, I've got time and I've got volume. In fact, wait a second. For our 30 mLs on this one, no, 40 mLs, we had 54 seconds. I had 88 when I did it last time. For 20 mLs, I had 25 seconds last time. But I did the timing and I've set up this spreadsheet. Learn how to use Excel because in lab calculations, it makes things so much easier. And I have plotted the volume of oxygen. I then calculated the moles. And for some way, I figured out how much hydrogen peroxide was being used in terms of moles. What equation would I use from volume of oxygen to moles of hydrogen peroxide? Yes.
And then multiply that by the hydrogen peroxide coefficient.
Yep, exactly. If this room was at 0 degrees Celsius and 760 torr, which is a weird temperature for standard temperature. If I wanted to be very exact, in fact, in this case, I was very exact. I'll open up my unhide my calculations. Unhide. I took the pressure of the room, 722. I adjusted for the height of the water because that water, as it was pulling down, changed the volume. And then I used PV equals nRT. And the PV nRT allowed me to calculate the moles. And this is where, again, if you get a chance, do learn how to use Excel. And I'm going to go and unhide. Let's see, let me undo that. And here's the concentration of the hydrogen peroxide as the reaction progressed. Notice we have a curve. If this had been a 0th order, this would be a straight line. But then, if you look here, when I plot the log, natural log of the hydrogen, the reactant concentration, I get a straight line. What can I determine using that straight line?
It's first order.
First order. And when I calculate the slope of this line and take the negative of it, what would I end up getting? If you find the slope of the natural log of a reaction of the reactants and you get a straight line, that slope will be equal to
The rate?
The constant.
Yes, the negative of the rate constant. I could give you the rate constant at this temperature for how fast hydrogen peroxide reacts with this amount of catalyst. Now, did the catalyst concentration change?
No,
No. Why not?
because it's not involved in the reaction.
Yes, it's not involved in the reaction. No. It is involved in the reaction.
Well, it gets reproduced back as a product at the end.
Oh, beautiful. Exactly. It is consumed somewhere in the reaction mechanism. That iodide ion is altered. And then along the chain, we make oxygen and it gets returned back to its original. It's like reincarnated. It's amazing. And so its concentration doesn't change at all. That's why your enzymes aren't used up. Enzymes are very, very powerful because they keep on reacting and reacting and reacting. And they're not used up until they're denatured. So catalysts are just amazing. They provide an alternate pathway and they stick around. They're regenerated. Beautiful, beautiful. Okay, now for some fun. We did our reaction rates. Here's another reaction rate demonstration. This is a classic. They don't do this much anymore because a lot of labs don't allow you to.
We cannot see the react.
Okay, there we go. Let me move that over. Good. Thank you for telling me that.
No, your camera's not flipped.
Oh, yes. Okay, good. Oh, yeah. Tell the teacher what to do. Oh, how insubordinate. Thank you. I'm glad you told me that. Let me flip the camera here. Camera's there. I'm glad you said that because this is one of my favorite things. This is a lab demonstration that used to be a classic in chemistry classes. It's the glowing splint demonstration. And as I said, they don't do this anymore because a lot of labs don't allow fire anymore. I'm going to take my match and get this splint. Every lab used to have splints that you would light. And I'm going to blow it out. And there it is glowing. Now, observez-vous. Not quite enough. Why did the splint burst into flame?
So
More oxygen?
Yes.
Is it
So
a combustion reaction?
it's the combustion reaction. And it was just glowing because air is 20% oxygen when we're a flask. Time.
The partial pressure of oxygen was increased.
Oh my goodness, I couldn't have said it better. When I had in this flask, the partial pressure of oxygen probably was about 0.2 of an atmosphere in air. So when that splint was trying to glow, it 4 out of 5 times it got some nitrogen. But in this flask, which had pure oxygen in it, all the collisions could have been with oxygen because the partial pressure of oxygen, this is pure, would be 1 atmosphere. And as a result, a glowing splint bursts into flame. So a pure oxygen environment, if you've got something that's glowing, you're going to be in trouble because it's going to burst into flames. That's a measure of concentration again. Here, we're dealing with reaction rates, a faster reaction rate because of a higher concentration of the oxygen. Now,